Hey there, welcome back to Calm Whispering Corner. We are about to journey through the cosmos and explore the wonders of the universe, all while keeping things calm and relaxing. Today, we're diving into some really cool topics in cosmology: relativity, the special theory of relativity, the general theory of relativity, and the mysterious and fascinating world of black holes. So, get comfy, close your eyes if you like, and let's float through the stars together. Introduction to Cosmology. Cosmology is the study of the universe as a whole, its origins, evolution, and ultimate fate. It's like trying to understand the biggest jigsaw puzzle ever, with pieces scattered across space and time. Imagine the universe as a huge cosmic playground, full of stars, planets, and mysteries waiting to be explored. Our journey begins with the Big Bang, the moment the universe was born about 13.8 billion years ago. Picture a tiny, incredibly hot and dense point, exploding and expanding into the vast cosmos we know today. This is the start of everything: space, time, and all the matter and energy in the universe. As the universe expanded, it cooled down, allowing particles to form atoms. These atoms clump together under gravity to form stars and galaxies. Over billions of years, these galaxies formed clusters and superclusters, creating the large-scale structure of the universe. Cosmologists use telescopes and other instruments to observe the light from distant galaxies, which helps them understand how the universe has changed over time. They also use theories and mathematical models to explain these observations and predict the future of the universe. One of the most intriguing questions in cosmology is about the nature of dark matter and dark energy. Dark matter is a mysterious substance that doesn't emit light, making it invisible, but we know it exists because of its gravitational effects on galaxies. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Understanding the universe is a bit like being a detective, piecing together clues from the distant past to uncover the story of everything. And today, we're going to focus on some of the most mind-bending aspects of this cosmic story: relativity and black holes. All right, let's start with the special theory of relativity, brought to us by the one and only Albert Einstein. This theory is super cool because it tells us that time and space are linked together in a four-dimensional fabric called spacetime. The special theory of relativity was published by Einstein in 1905, and it revolutionized our understanding of physics. Before Einstein, people thought that time and space were absolute, the same for everyone, everywhere. But Einstein showed that they're relative and can change, depending on how fast you're moving. One of the key ideas in special relativity is that the speed of light is the same for everyone, no matter how fast they're moving. This means that if you're in a spaceship travelling at half the speed of light, and you shine a flashlight ahead of you, you'll still measure the light from the flashlight travelling at the speed of light. This constancy of the speed of light leads to some surprising consequences. For instance, let's talk about time dilation in a bit more detail. Imagine you have a twin and you go on a journey through space at close to the speed of light, while your twin stays on Earth. When you return, you'd find that you've aged much less than your twin. This is because time has been passing more slowly for you on your high-speed journey. This is known as the twin paradox. Another consequence of special relativity is the famous equation E as mc2. This equation tells us that energy and mass are equivalent. They're just different forms of the same thing. This means that a small amount of mass can be converted into a huge amount of energy, which is the principle behind nuclear power and atomic bombs. Special relativity also changes our understanding of space. As we mentioned earlier, objects moving at high speeds appear shorter in the direction of motion. This effect, known as length contraction, has been confirmed by experiments with particles moving close to the speed of light. One of the most fascinating aspects of special relativity is that it unifies space and time into a single entity called spacetime. In this four-dimensional spacetime, events are described by 4 coordinates, 3 for space and 1 for time. This idea has profound implications for our understanding of the universe. Special relativity is a beautiful and elegant theory that has been confirmed by countless experiments. It's essential for understanding the behaviour of particles at high speeds and for many modern technologies, like GPS, which relies on precise measurements of time and space. The general theory of relativity. Einstein didn't stop there. He also gave us the general theory of relativity, published in 1915. This one's a bit more complex, but let's break it down. Imagine space-time as a big, stretchy trampoline. If you put a heavy ball on it, the trampoline bends. This bending is similar to how massive objects like stars and planets warp space-time. The general theory of relativity is a theory of gravity. Before Einstein, the best theory of gravity was Newton's law of universal gravitation, which described gravity as a force between 2 masses. But Einstein showed that gravity is actually the result of the curvature of space-time, caused by mass and energy. In general relativity, massive objects like the Earth or the Sun cause space-time to curve around them. This curvature affects the motion of other objects, causing them to move along curved paths. For example, the Earth orbits the Sun because it's moving along a curved path in the curved space-time around the Sun. One of the key predictions of general relativity is the bending of light by gravity. This was confirmed in 1919 when astronomers observed the light from stars being bent by the Sun during a solar eclipse. This bending of light is called gravitational lensing, and it's now a powerful tool for studying the universe. General relativity also predicts the existence of black holes, which we'll talk about in more detail later. Black holes are regions of space-time where the curvature is so extreme that not even light can escape. They're formed when massive stars collapse under their own gravity. Another fascinating prediction of general relativity is the expansion of the universe. In the 1920s, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, indicating that the universe is expanding. This expansion is described by a solution to Einstein's equations called the Friedmann-Lemaitre-Robertson-Walker metric. General relativity also predicts the existence of gravitational waves, which are ripples in space-time caused by accelerating masses. These waves were first directly detected in 2015 by the LIGO experiment, providing further confirmation of Einstein's theory. General relativity has been confirmed by many experiments and observations, from the precise orbits of planets to the behaviour of light in strong gravitational fields. It's a cornerstone of modern physics and essential for understanding the behaviour of the universe on large scales. Imagine a star that's supermassive, much bigger than our Sun. When it runs out of fuel, it collapses under its own gravity and forms a black hole. These black holes have such strong gravity that not even light can escape them, hence the name black hole. Black holes come in different sizes. There are stellar mass black holes, which form from the collapse of massive stars and are a few times the mass of the Sun. Then there are supermassive black holes, which are millions or even billions of times the mass of the Sun and are found at the centres of galaxies, including our own Milky Way. The edge of a black hole is called the event horizon. Once something crosses this boundary, it can't come back. It's like the ultimate point of no return. The event horizon is defined by the Schwarzschild radius, which depends on the mass of the black hole. Inside the event horizon, the gravitational pull is so strong that not even light can escape. This is why black holes appear black. No light can get out. But black holes aren't completely invisible. We can detect them by their effects on nearby matter. For example, gas and dust falling into a black hole can heat up and emit X-rays, which we can observe with telescopes. One of the most mind-bending things about black holes is the singularity at their centre. This is a point of infinite density where the laws of physics, as we know them, break down. The singularity is hidden from view by the event horizon, so we can't directly observe it, but it poses fascinating questions for theoretical physics. Black holes can also merge with each other, producing powerful bursts of gravitational waves. These mergers have been detected by the LIGO and Virgo observatories, providing new insights into the properties of black holes and the nature of gravity. Another intriguing possibility is that black holes could be gateways to other parts of the universe, or even other universes. This idea, while speculative, is a topic of active research and could lead to new understanding of the nature of space and time. Black holes are not just cosmic vacuum cleaners. They play a crucial role in the evolution of galaxies. For instance, the supermassive black hole at the centre of our galaxy, known as Sagittarius A, influences the motion of stars and the structure of the Milky Way. Fun with relativity and black holes. To make things more fun, let's imagine what it would be like to visit a black hole. If you fell into a black hole, not recommended for your next vacation, time would get really weird. From your perspective, time would seem normal, but to an outside observer, you'd appear to slow down and freeze as you approach the event horizon. It's like being in a cosmic slow-motion movie. And here's a humorous thought. If you tried to send a text from inside a black hole, your message would never reach your friends. "Hey, I'm stuck in a black hole. Send help," would just hang there forever. Talk about poor reception. But let's dive deeper into what happens as you approach a black hole. As you get closer, the gravitational pull gets stronger and stronger. If your feet first, the difference in gravity between your feet and your head would stretch you out like a piece of spaghetti. This effect is known as spaghettification, and it's as unpleasant as it sounds. Inside the event horizon, the curvature of space-time becomes extreme. The paths that light and objects can take are bent so much that all directions eventually lead to the singularity. It's like being in a maze where all paths lead to the same dead end. If you were to observe a black hole from a safe distance, you'd see some fascinating phenomena. For example, the intense gravity near the event horizon can bend light around the black hole, creating a ring of light known as the photon sphere. This bending of light can produce amazing visual effects, like multiple images of the same star. Black holes can also have powerful jets of particles shooting out from their poles. These jets are created by the intense magnetic fields around the black hole and can stretch for thousands of light years, blasting out energy at nearly the speed of light. One of the most amazing discoveries in recent years was the first image of a black hole's event horizon, captured by the Event Horizon Telescope in 2019. This image showed the shadow of the supermassive black hole in the galaxy 87, surrounded by a glowing ring of hot gas. It was a groundbreaking achievement and provided new insights into the nature of black holes. Another exciting area of research is the possibility of black hole evaporation. According to a theory proposed by physicist Stephen Hawking, black holes can slowly lose mass and energy through a process called Hawking radiation. Over incredibly long timescales, this could cause black holes to shrink and eventually disappear. Exploring the universe of black holes and relativity opens up a world of fascinating questions and mysteries. It's a reminder of how much we still have to learn about the cosmos and the fundamental nature of reality. And that's our journey through the fascinating world of relativity and black holes. I hope you enjoyed this cosmic adventure and learned something new. Remember, the universe is full of wonders waiting to be explored, and each discovery brings us one step closer to understanding the grand puzzle of existence. Thank you for joining me on Calm Whispering Corner. Don't forget to like, subscribe, and hit the bell icon so you don't miss our next relaxing exploration. Sweet dreams and cosmic thoughts.